Hello there. It's no exaggeration to say that you're going to like hyperbolas, our last conic section in this series of videos about our conic sections. Hyperbolas can often be one of the trickiest conic sections to do because they're asymptotes that are involved and that can be a little bit tricky. All right, but we're going to go right through it and you'll be experts by the end of this. So we got 4 examples to look through and to try to figure out what's going on with our third conic section, which is the hyperbola. Just as a little reminder, the conic section is that figure that we form when a plane intersects a double right cone. Okay, so we've seen parabolas, we've seen ellipses, circles are basically a type of ellipse, and now we see the hyperbola. So our plane intersects the cone both on the top and on the bottom, and so we get 2 branches, or what we're going to call this, of what's called a hyperbola. So let's investigate what this hyperbola looks like. The formal definition is that a hyperbola is the set of all the points, so the difference of distances between 2 fixed points is constant. It's hard to represent that here, and I'm not going to go into too much depth with that definition, but basically every point that's here on the green curve, if we were to take that point and go all the way to the focus here, that would be a pretty long length, and then we get a short length right here on the left. And when we subtract those those distances, we're going to get a constant. But the big key is that the word difference is involved in here, and so that's what's going to help form our equation. So 2 equations to look at, just like with the ellipses. The first equation is x minus h squared over a squared minus y minus k squared over b squared is equal to 1. All right, so notice right here that the x is a positive term and the y squared is a negative term. That's going to be important. And in fact, it's going to tell us which way that this particular hyperbola is going to open. If the x is the positive term here, that means we're going to open to the left, all right, and to the right. So we have a branch that opens to the left and a branch that opens to the right. All right, as we'll see in just a second, if it's reversed, then we're going to open up and down instead. What we'll call this is what's called the transverse axis. So the transverse axis is this axis that runs right through the vertex and the focus on either side here. We also have what's called a conjugate axis. The conjugate axis is the axis that's perpendicular to our transverse axis. But we don't need to know too much of the terminology. I just wanted you to be familiar with this. So the transverse axis is this axis that actually shows which direction the hyperbola is opening. It's horizontal in this case. Center at h comma k, just as like with ellipses and parabolas. I want you to note that the a always represents the distance from center to vertex. All right, people sometimes get a little confused about that. The a is not always the biggest number. It is for an ellipse. That's only because the vertex is the farthest out from our center in an ellipse. But if you notice our particular graph right here of the hyperbola, the focus is actually further from the center than the vertex. That's what makes this unique. Okay, so the vertex is actually closer than our focus is to the center. So a might not always be the largest value for a hyperbola. It could be, but not always. It's always the distance from the center to the vertex. That means, all right, that our vertices in this particular case is we take our h value, our x coordinate, and we add a to it to find our vertex. For foci, we add our c value just like before. So a is the distance from center to vertex. C, as before, is the distance from center to foci. It's further out for the focus. And our asymptotes are the equation y minus k is equal to plus or minus b over a times x minus h. Now, this looks really, really complicated, but in fact, all we're doing is we're shifting our asymptote over h comma k to where our center is. And then b over a comes from the fact that b is associated with the y and a is associated with the x. The slope is always what's with the y over what's with the x. It is in regular terms, right? Change in y over change in x. B is with the y, that goes on top here. A is with the x, that goes on the bottom. So there are our asymptotes. And then finally, c is now the biggest value. All right, so unlike with the ellipse, in this case, c squared is equal to a squared plus b squared. C has to be the bigger value, so a and b both add up to get there. So in a hyperbola, it's like we've destroyed the ellipse. And on the ellipse, the foci were inside the shape. Now the foci are far out and outside the shape, and I'll show you with an example in class. All right, so same sort of idea, equation number 2, y minus k squared over a squared minus x minus h squared over b squared is equal to 1. A minus because it's a difference. Notice the y is out front, so this makes us a vertical transverse axis, so it opens up and down instead, opens in the vertical direction. Center at HK, A is always in front, so notice that it's right here and right with the y. And so our vertices are H, comma, K plus or minus A. Foci are H, comma, A plus or minus C. And then our asymptotes, notice the only thing that changes here is now the A is with the Y, so the A goes on top. Change in Y over change in X. So A is with the Y, B is with the X. And then again, C squared is equal to A squared plus B squared. So let's start with a couple of simple examples that are not shifted. Silly me, graph the hyperbola given by the equation x squared over 81 minus y squared over 49 is equal to 1. Identify vertices, foci, and asymptotes. So, first thing we want to do, find h, k, a, b, and c. So h, there's no shift. We're starting out easy, so h equals 0, k is equal to 0. So the center is at 0, 0. A is always what's out front. It's what's with the x in this case. So a squared is equal to 81, so a is 9. B is the second part of this after the subtraction sign, so b is equal to 7 because b squared is equal to 49. And then we know that a squared and b squared have to add up to equal c squared. So we add the two of them in this case to find where c is. So that makes c squared equal to 130. So c is the square root of 130. We find the orientation. Since x squared is in the front, this is going to open horizontally. That transverse axis is the x-axis in this case. All right, so we get a picture that looks like that. So in order to find out what's going on, our vertices, foci, and asymptotes, A always tells us what's happening with the vertices. So we have a vertices going 9 to the left and 9 to the right. So at negative 9, 0 and 9, 0, use A. Foci in the same direction. So we get plus or minus square root of 130, comma 0. So that we use C there. And then our asymptotes are y equals plus or minus b over a. Why b over a? Well, in this case, b is with the y and a is with the x. So whatever's with the y goes on top, just like slope. So 7 is b and a is 9. So we get y equals plus or minus 7/9 x. And you can see those asymptotes drawn right there. We'll talk in class about how to use a particular method to graph these quickly, but just rely on this for now. Graph the hyperbola given by the equation y squared over 4 minus x squared over 5 is equal to 1. Identify vertices, foci, and asymptotes. Notice this is another one that's not shifted. So h equals 0, k is equal to 0. A is always with the front term, the positive term, so a squared is equal to 4, a is equal to 2. But notice now a is with the y, so that's going to make a difference here. That makes b squared equal to 5, so b is equal to square root of 5, b is with the x. C squared is the sum of a squared and b squared, so c squared is 4 plus 5, which is 9, so c equals 3. Find the orientation. Since y squared is in the front in this case, this hyperbola is going to open up. All right, opens vertically. And then that means that to find the vertices and foci, we're going to do all that with y. So a is equal to 2, so we can go down 2 and up 2 from our center of 0, 0 to find our vertices. So we get 0, negative 2 and 0, 2. And then our foci are at 0, 3 and 0, negative 3, because that's what our C value is. In this case, the asymptotes are A over B. Well, why is that? A was with the Y, because it was out front, and B is with the X, because that was after the negative sign. So Y is equal to plus or minus 2 over square root of 5x, or 2 root 5 over 5x. All right, so we get our two asymptotes right here, and the hyperbola fits nicely right in between those asymptotes. The same problem here, except, all right, we have y plus 4 squared over 4 and x minus 2 squared over 5 equals 1. So same idea right here. You get the same values except for h and k. So I'm using the same values a, b, and c for this one. All right, so h is equal to 2. That's our change in x, and k is equal to negative 4. Y squared is still in front, so this opens vertically. The only question is how do we find the vertices, foci, and asymptotes? Well, all you got to do is you got to take your h and your k, and you add a and b or a and c to whatever you get. So initially, our center is at 2, comma negative 4. You can see that right here on the graph. So to find our vertices, what I'm going to do is I'm going to add and subtract a to my y coordinate. When I do that, I get 2 comma negative 6 and 2 comma negative 2. So all I did was I shifted everything to the right 2 and down 4. All right, so we went to 2 comma negative 2 because 2 comma negative 4 minus 2 and 2 comma negative 4 plus 2 will give us our new vertices. Okay, we do the same thing. We take our center of 2 comma negative 4, and we're going to subtract 3 and add 3 to our y coordinate, and we get new foci of 2 comma negative 7 and 2 comma negative 1. Our asymptotes, same sort of idea. So in this case, we need to shift. We're going to go to y plus 4, because that's what's inside the parentheses, really, and x minus 2. That's what's inside the parentheses, so it accounts for our shift. So get y plus 4 equals plus or minus 2 over root 5, comma x minus 2. So it's the same graph that's been shifted over to a new center of 2 comma negative 4. Last problem here, write an equation for a graph of a hyperbola that has the following characteristics. Vertices at negative 6, negative 3, and 2, negative 3. Foci at negative 7, negative 3, and 3 comma negative 3. So we know that this hyperbola is oriented horizontally. If you were to actually kind of sketch these points out, you'll notice that what's changing is the x. So our vertices and our focus are all on our horizontal axis. So we have a change in the x direction. And the center is right in between the vertices. All right, so halfway in between would be at negative 2 comma negative 3. So halfway between negative 6 and 2 is negative 2. So how can we figure out A and C and B? Well, the value of A is the distance from vertex to center. So that distance, like let's say from x equals 2 to x equals negative 2, is a distance of 4. The value of C is the distance from foci to center. So that distance is 5 when you look at negative 7 and negative 2. So A squared has to be 16, and it's going to go with x. We have a change in the x direction. C squared is equal to A squared plus B squared. C squared is equal to 25, and A squared we already know is 16. So B squared has to be 9, and that's what's going to go with the y. So all together, we get x plus 2 squared, because our center is at negative 2 with our x coordinate, over 16. So A squared is 16. It always goes out front. Minus y plus 3 squared over 9 is equal to 1. So A is equal to 4. So A squared is 16, B is equal to 9, so B squared, or B is equal to 3, so B squared is 9. And X goes out front. All right, in summary, hyperbola is the set of points so that the difference of distances from two fixed points or foci is constant. Different equations can be used to describe hyperbolas horizontally or vertically, and then the asymptotes do help to define the shape. We'll talk about that a little more in class when we draw them by hand. We'll see you soon.